What holds atoms together in a molecule or in the smallest unit of a compound? Well, we're probably used to the answer to that. It's a chemical bond. What we probably aren't as familiar with is the effect that those bonds have on the properties of the compounds. Here we have three different, what are called allotropes of carbon. There are three different forms of carbon that all depend on how the carbon atoms are bonded together. So on the left we have a diamond, and obviously one of the hardest substances known. In the center we have coal, or it's kind of technically called an amorphous form of carbon used in the production of electricity. And over on the right, we have graphite, which is used in our pencils. Our pencil, quote, lead is actually graphite. All three of these have carbon atoms that are bonded together in slightly different ways, resulting in, obviously very different properties. This website has another interesting application of how the bonding in a molecule can affect the properties of that compound. So it'd be worth taking a look at that as well. So to expand our knowledge and understanding of the chemical properties, we need to get into what's the nature of these bonds. There are different types of chemical bonds that we'll talk about. There's something called electronegativity, which is a property of the individual atoms within an element. These are going to play a role in the type of chemical bonds that occur. Then we'll look at the bond polarity and dipole moment. This has to do with how the electrons in an atom or atoms that are bonded together are going to orient themselves. We'll go back and look a little bit at the stable electron configurations and charges, talk about ionic bonding, Lewis dot structures, and eventually we'll get to where we can talk about the three-dimensional molecular structure of substances and start to get to the point where we can try to understand the function and the properties of molecules and how the structure affects those properties. First, let's take a look at a chlorine atom. So the electron configuration for chlorine. Chlorine has 17 electrons. And so if we use our chart of atomic orbitals, we would say it's a 1s2, 2s2, 2p6, 3s2, 3p5. And we know that the highest principal energy level is the valence shell, so that would be the third energy level. So we get to count both the s's and the p's. So chlorine has 7 valence electrons. So chlorine's in a situation where it will tend to want to gain 1 electron to become like argon, which has 18 electrons. And the 18th electron would make that a 3p6, and it would be a full valence shell. Well, where's it going to get that electron from? Well, our most common element that could donate this to chlorine would be sodium. Sodium atom has 11 electrons. So that's a 1s2, 2s2, 2p6, 3s1. And so that 1 electron, that 1 valence electron on the sodium could be donated to the chlorine, so that chlorine would then have a full valence shell. And you can see that would leave, if we eliminate the 3s from the sodium, sodium would then have a full valence shell. When you have a situation like this, where you have a metal that tends to have very few valence electrons and a nonmetal that has a significant number of valence electrons, you tend to get what's called an ionic bond. In the ionic bond, the metal is going to lose electrons to the nonmetal. Now, what holds this together? Well, the electrostatics of this. So when the metal loses the electron, it takes on a positive charge. When the nonmetal gains an electron, it takes on a negative charge. The positive ion is called the cation, and the negative ion is called the anion. And positives and negatives are going to attract. It's that attraction between the positive and the negative that we refer to as an ionic bond. Okay. Ionic bonds are very strong. That attraction is rather strong. So most ionic substances at room temperature and room pressure are going to exist as solids. They're one of the properties that of this strong bond is that you have to go up to a very high temperature in order to change an ionic substance into a liquid and even more so into a gas. Just a brief review. Recall that if we draw a diagonal line down this part of the periodic table, we make a kind of a general separation between the metals to the left of that line, and the farther we go to the left, the more metallic it is, and the nonmetals that occupy the upper right-hand corner and include the noble gases, the last column here in yellow. So it's kind of a reminder of the things that we classify as metals and nonmetals. Obviously, the nonmetals are a much smaller group of elements. If we put two nonmetals together, remember that nonmetals are going to have, in general, have more valence electrons, and so they are looking to, both nonmetals will be looking to gain electrons in order to fill up their outer shell, which obviously presents a problem. How does both atoms gain electrons? Well, what ends up happening is that those atoms are going to come together, their electrons will interact, and there will be a type of sharing that will occur in order to form what's known as a covalent bond. So here we have two hydrogen atoms that are separated over on the left, and as those two hydrogen atoms come together, the interaction of the electron densities between the two, and realize each one only has one electron, but the field, the electron density as it interacts between the two, each molecule is going to, in a sense, get that feel like it has a full valence shell, which for hydrogen is just 2 electrons. It only has to fill up that 1s orbital. Now, what's holding the atoms together in a covalent bond? Well, if we take a look at the nuclei for each of the 2 hydrogens that are bonded together, and if we think about that electron as a point in space rather than as a wave for just a moment, we have an electron there and an electron here. Both of them are being shared, or the electron density is located between the 2 nuclei. It might be a better way to think about it. But those electrons are attracted to both nuclei. Right? So all that electron density that we're putting between the 2 nuclei, the 2 hydrogen atoms, are going to be attracted to both atoms. It's that attraction that's referred to as a covalent bond. And covalent bonds, again, are rather strong. The bonds that hold carbon atoms together in a diamond, very, very strong. Obviously one of the hardest known substances. So these type of bonds can be as strong, if not stronger, than ionic ones. In some cases, they can be weaker as well, but in general, the covalent bond is a very strong bond as well, similar to the ionic bond. In the case of the hydrogen molecule, both atoms that are sharing electrons are of the same type. They're both hydrogen atoms. If we look at something that's a little bit different, if we take a hydrogen atom and a fluorine, so again, 2 nonmetals, and we bring those close together, you get that same interaction of the electrons, that same sharing that's going to happen. But in this case, fluorine, because of the atomic structure, fluorine actually is much better at pulling on that shared pair of electrons. And so you get a greater amount of electron density from that shared pair going toward the fluorine. And so we create a partial negative charge and a partial positive charge. Partial negative being on the fluorine, partial positive on the hydrogen. It's just a partial. It's not the same as an ionic bond, so we don't draw literally a plus and a minus, but there is a difference in the distribution of the electrons within this molecule. This is referred to as a polar covalent bond. You can think of poles of a magnet or poles of the Earth where you have one side that's negative, one side that's positive. Right? So within this bond between the hydrogen and fluorine, you have one element that tends to take more of a negative charge and one that takes more of a positive charge. Here we have the periodic table, but instead of having masses and atomic numbers on there, we have electronegativities. The electronegativity is a measure of the element's ability to, or atoms of that element, to pull on a shared pair of electrons. So for instance, in the one we just had, we had hydrogen and fluorine. And so you can see that hydrogen has an electronegativity of 2.1, fluorine has an electronegativity of 4.0. There's a pretty significant difference in the electronegativity there, which is, the result of that is that the electrons that are being shared are pulled more toward the fluorine. If we look at another common molecule, say H2O, and we should all be familiar with the structure for water, and the electronegativity again of hydrogen is 2.1, oxygen is 3.5, so the difference here is 1.4. Am I correct? 1.4? Which means that the electrons that are being shared, which are represented by the dash here between the oxygen and the hydrogen, are being pulled more toward the oxygen than the hydrogen. So I can draw these arrows showing that the electron density is moved more toward the oxygen. This makes the two bonds in the water molecule polar and accumulates a bunch of negative charge around the oxygen, which ends up being a pretty significant in terms of determining the properties of water. So here's kind of a summary then of what we have here. If you have by looking at the electronegativities, if you have a zero difference in electronegativity, you tend to create, two atoms come together more of an equal sharing of electrons. So these would be, taking two nonmetals, the same element together. So a Cl2 or an N2, you'd have zero difference in electronegativity, and so you get an equal sharing of the electrons that are involved in the bond. If there's a slight difference in electronegativity, then anywhere from a 0.5 to a 1.7, 1.8, then you would have a situation like this where the bond would be polar covalent, and so there would be more electron density around the element with the higher electronegativity, and a positive part around the element with the lower electron density, electronegativity. And if you had a large enough difference in electronegativity, for instance, if you had a metal with a nonmetal, metals tend to have very low electronegativities, nonmetals have high electronegativities, then when those electrons start to go together, they're actually transferred. So that's a little bit more of a sophisticated way of thinking about an ionic bond, rather than just metal and nonmetal, the metal giving electrons and nonmetal taking electrons. You might think about it in terms of the electronegativity, and the electronegativity on the nonmetals being so much larger that when they come together, they're able to pull electrons away from the metal and create the ionic bond. So that's our introduction to the basics of bonding. The next step will be to try and understand a little bit better about how the electrons are arranged within molecules that have more than two atoms.